basically the error here, the squared error between your prediction and your actual value. And you do feature engineering to get your X's from your data. And a lot of what you do when you get started is just going to be regression. So it's important to be familiar with it. From there, if you want a more complicated F here, you can look into something like a support vector machine, support vector regression, for example. You can do random forests. There's all these other models, these nonlinear models that you can use that have more complicated representations of F. In a random forest, you don't even really know what F looks like. You know, it's because it's a bunch of random trees basically to predict stuff. In a neural network, a neural network can approximate any F, theoretically speaking. So neural networks, you know, there was a proof in 1994. This guy Sabento came up with this universal approximation proof that if you have any F, like any set of data with features, you can approximate any F with a neural network. In practice, that's not necessarily true. There's a lot of practical problems when it comes to neural networks. So the basic predictive machine learning problem is, given a set of features X, like a vector of features, an array of features, and some output variable Y, I want to predict Y from X, but I have to give it a bunch of data to train it on first. And that's called a supervised learning problem. So when it's a supervised learning problem, you know what your output is supposed to be given your inputs. And you have a bunch of training data. And the goal is to give it fresh data and then predict basically what, you know, the output should be given your fresh data. And that's the predictive part of it.
Can you give an example of a body of data and features in the training?
Yeah, so...
Like how about the zebra in a photo example you gave earlier?
Move away from images for a second.
Gesture recognition. Gesture recognition.
Gesture, we'll go to images in a second. One simple example is like medical data. Like, we want to predict what is the probability that somebody is going to get diabetes, given their blood pressure, regular blood sugar readings, so on and so forth, right? So your features are going to be like blood pressure, average blood sugar, something like that, age. So you have that, and then the output variable Y is actually going to be equal to 0 or 1, right? Because it's either they have diabetes or they don't, right? But what you're actually going to predict, use the method called logistic regression. If you wanted to do regression, use the method called logistic regression to fit that model. Take your input features and train on your data. But the prediction from the logistic regression model is actually a probability of a person getting diabetes, which makes it actually pretty effective. You can also, for a classification problem, support vector machines are very popular. Just to be clear again, the difference between classification and regression. Classification is when you have an output variable that is like a discrete entity, like a category. And regression is for when your output variable is like a number, like a real number, between negative infinity and infinity, but hopefully less, more compact. So yeah, so in a binary regression, or a binary classification problem, like we were just talking about diabetes or no diabetes, you would use logistic regression. If you want to look that up, it's logistic. With image classification, yeah, your input, if you wanted to do raw input for an image, it would be, you would take the pixels, and it's like a matrix of numbers, and then you just take the matrix and reshape it into a vector, like a long array, and then you can do regression on that long array. So if you wanted to predict, is there a face in this picture or not? Another binary classification problem. Your features change. Your features are just images. In practice, you're not going to just take a raw image and do classification on it. There's problems with scaling. You know, if you're trying to place it on whether a face is there, and like the face is like here as compared to here, it's going to be a different size. You need some scaling variance and a lot of different pre-processing, it's called, to get the right features out. One thing for image classification that people have classically used is SIFT features. So you can look that up if you want, and that's a method of pre-processing an image to get features out of it so that you can do stuff on it, typically like a regression or something simple. You always start with, my opinion is that you should always start with regression. If you come in and you're working for somebody or you're working on a new project and you have no baseline, like you don't know how well a model can predict in the first place, always start with regression and see how well you can do in the first place with regression, and then move on to more complicated models like a random forest or a sport vector machine or whatever.
You mentioned another regression, I think it was mythical.
What was it?
Mythical regression, you say? No.
Logistical?
No.
Logistic
I heard the
regression.
word mythical.
Mythical regression.
That's the
Yeah,
one that
like
works
a
all
bunch
the
of
time.
Unicorns, and you're trying to like.
No, you said something that sounds like mythical.
Logistic regression. SIP. Did I SIP?
No, mythical. I was expecting you to say it again.
He's talking about
Maybe
medical
I will.
at one point.
No, I remember there was myth something
Hmm.
that I didn't understand the word.
Meth regression, like Breaking Bad sort of thing. Like you're looking for a drug dealer.
What was the context?
I think regression is
Prediction?
Mathematical.
Mathematical maybe? Classification?
I don't know. Maybe it'll come up again. I tend to repeat myself, so I don't know. Does anybody have any just general questions? I'm happy to just talk. I'm sure there's, there's definitely people here that know some stuff.
Can you explain the neural networks in global general point of view? What is neural
Can
network?
we do a simple example of logistic of how the logistic regression works? Like with just one input? Like I thought in the scenario, if you wanna like make fake data, like how, like year of birth and do you have Snapchat on your phone? And then you could put a bunch of no's, with the like older birth and like a bunch of yeses, right? And then your dot, you're like, you can make a graph. You have a whole bunch of dots down here and a whole bunch of dots up here, right? You just do 0 and 1.
Yeah.
Okay, so then so now go. Now finish the example.
All right, so let's take that example.
You can draw it.
Age, yeah, I'm gonna take it.
Okay, sorry.
So,
I can draw it, should I draw
Yeah,
it?
go ahead.
Do you have
Just
the-
basically, I think.
This is my idea. Where should I end, like 1990? That's
Age.
Yeah, 97.
Well, if it was age, I would just do
How
like,
about the year 2000? Those are 13-year-olds. They have phones,
I'll
right?
get their actual age in that census.
Oh, okay, that's probably. Anyway, so the. Maybe like switching over. Should I make it like structure?
That's good.
Something like
Yeah,
that,
that's
right?
good, yeah, very good idea. What it would be like, another way of plotting this data would be to make a histogram. And then on your histogram, if you don't know, should bring this, yeah. So, say on your histogram, you have age, and then you have two different distributions on your histogram. The red distribution will be yes, they have Snapchat, and the blue distribution will be no, they don't. So you have two histograms, you plot them in the same plot, and you might see something like this. So blue is no Snapchat, red is yes, they have Snapchat. The difficulty when it comes to this is this part right here.
Mm-hmm.
So this is, this is the, if you have a logistic regression classifier, this part here is called the decision boundary. So you want to pick the right decision boundary so that it separates out these two distributions properly. But yeah, for a first cut at that data, you can definitely just make two histograms and just look at it and say, is this even, if it's so clear, if it's like that, you will surely just train a logistic regression classifier and it will work very well.
So then what you would do is you would put in, you'd be like 14, and then what would come out is the chance of having Snapchat. It'd be
Yeah,
like
first-
90.
Well, you get all this data, right? Your data's gonna look like this. It's gonna be
29,
like,
15% chance.
it's gonna be like 13, 1,
Right.
12, 0, 22, 1, 43, 0, so on and so forth. This is your training data. And you pass it into a function, basically. You create a matrix from this or something. Matrix of 2 arrays, and then you pass it to, use software called scikits.learn. Scikits.learn is an excellent package. It's definitely grown over the years. It has a lot of different implementations of logistic regression that do various forms of things. And there's a logistic regression class. You create it, you pass it your data to train. There's a training function called train. You pass it your data. And then there's a predict function. You have new data, you predict an age. The predict, I don't know if predict is going to return a probability or if it's going to return a 0 or 1. With logistic regression, when you usually, if you want to turn it into a binary thing, you're going to threshold your probability. So if the probability is over 0.7, then it's definitely a 1. If it's less than 0.7, I'm just going to assume it's a 0, for example. And there's a whole thing about what the right threshold should be and stuff like that. It's a whole kind of art unto itself. So yeah, that would be a logistic regression problem for the Snapchat issue.
Because the example where you have like many X's is really hard to imagine.
Yes.
But one X.
One way to visualize a two-dimensional example, people usually use with support vector machines to illustrate how they work, is, and you'll see this